In this video, I want to show you what I made using the HC-SR04 ultrasonic sensor with Raspberry Pi Pico. We will also go step by step through the hardware connections, MicroPython code uploading steps, and the projects I created. I will cover all the details, but before we get started, don't forget to like the video and subscribe to the channel. If you're ready, let's take a look together at what parts we need for this project. We are starting with our first component, the HC-SR04 ultrasonic distance sensor. It measures highly accurate contactless distance by sending high-frequency sound waves to obstacles and collecting them back. This allows us to easily gather the main input data needed for our entire system. Next up is our 2.8-inch SP-IT-FT LCD screen with a resolution of 240 by 320. We will use this display to track all our data, graphics, animations, and the menu interface in real time with absolute precision and clarity. Another key component is the passive buzzer, which adds audio capability to our system. With this module, we can generate various tone frequencies, warning alarms, and sound effects to get audible feedback across our projects. And of course, at the very core of our system is our main processing unit powering the entire project, the Raspberry Pi Pico 2. Driven by the powerful dual-core RP2-350 microcontroller, this high-performance board allows us to process real-time sensor data while managing display graphics and buzzer sounds simultaneously with complete ease. To control the system, we are using two 12 by 12 mm tactile buttons. While you can directly use the internal pull-up resistors of the board, you can also opt to add external 10K resistors to your circuit. These buttons allow us to easily navigate through the menu projects and select any application we want. And finally, I'm using this breadboard to safely connect all these components together without any soldering. I'll build all the circuit connections right here on this board to bring our project to life. Why am I using a breadboard? I want this video to be educational. By building it modularly, you can see how each component connects in real time. I'll show the pinout table on screen, and you can find the GitHub repository in the video description for all the code and setup details. Alright, now let me show you how we place all these components onto the breadboard. First, we plug in our ultrasonic distance sensor. Right next to it, we position the TFT display module firmly into place. Next up, we're inserting the absolute brain of our entire project, the Raspberry Pi Pico, right into the center of the board. Be careful not to apply too much pressure here to avoid bending the header pins. Just push evenly until it fits securely. Right beneath it, we carefully press in our active buzzer module. Now, we're placing two 12 by 12 tactile push buttons right onto the board. Make sure their legs straddle the center divider properly, then press down gently until they seat firmly into the breadboard. These two buttons will give us full interactive control over our project's user interface. Now, I'm temporarily removing the TFT display from the breadboard. As you can see, all the pin labels are printed right on the back of the module. I'm taking it off so we can clearly check these labels and compare them with the pinout table on the screen before we start making any of our jumper wire connections. Now we're moving on to the wiring process for our 2.8-inch TFT SPI display. As you can see on the right side of the screen, I've put up the full pinout table so you can easily follow along step by step. To keep the video moving along, I've fast-forwarded the wiring process. Just refer to the pinout table on the screen to connect each jumper wire to its corresponding pin at your own pace. First, let's focus on the power connections. I'm plugging in the power lines right here on the breadboard, connecting VCC to the Pico's 3.3 volts output and GND to a common ground line. Once the power setup is ready, we'll start wiring the SPI communication lines, CS to GPIO17, reset to GPIO15, and DC/RS to GPIO14. After that, we'll connect our main SPI data pins. SDI/MOSI goes to GPIO19 and SCK/CLK to GPIO18. Finally, don't forget to connect the backlight pin LED/BLK to 3.3 volts so the screen stays brightly illuminated. Take your time with these jumper wires and double check every pin against the table on the screen before plugging the display back in. Now that all the display wiring is completely finished, we can safely place the TFT screen back onto the breadboard. Make sure to press down evenly so that all the header pins make proper contact. This keeps our entire setup tidy, compact, and ready for the remaining component connections. Next up, we are connecting our passive buzzer module. First, we connect the ground pin of the buzzer to the common GND line on the breadboard or directly to pin 23 on the Pico. Then, we wire the signal pin to GPIO22. We specifically chose GP22 to avoid hardware conflicts with SPI0. Finally, we connect the power pin to the 3.3 volt output on the Pico. Now our buzzer is fully wired and ready to generate audio signals for our project. First, I am carefully removing the ultrasonic distance sensor from the breadboard so we can access the pins easily. Now we are placing the GND wire and connecting it to the common ground line on our board. Next, we are taking the echo wire and connecting it directly to GPIO2 on the Pico. After that, we are placing the trig wire and plugging it securely into GPIO3. And finally, we are connecting the 5-volt power wire to the VBUS pin to power up the ultrasonic sensor, completing the module wiring, and then we place our sensor back onto the breadboard. Now we are moving on to the push-button connections for our user interface. First, to keep our wiring clean and efficient, we are bridging the ground legs of both push buttons together on the breadboard and connecting them directly to the common ground line. Once the ground connections are done, I'm taking a quick look to make sure everything looks good. Next, we wire the signal cable for our navigation button to GPIO21 on the Pico. After that, we connect the signal cable for our select button to GPIO20. Since we will be using internal pull-up resistors in our code, these connections complete our button setup. And finally, now that all the hardware wiring is complete, we are ready to set up our board. First, make sure the USB cable is plugged into your computer. Next, press and hold the boot cell button on the Pico while plugging the USB cable into the board. This puts the Raspberry Pi Pico into bootloader mode, getting it completely ready for code upload via Thonny IDE. We open the Thonny IDE application on our computer. If you haven't installed it yet, you can simply search for it on Google and download it. The installation process is very quick and easy. Once Thonny is open, we click on Install MicroPython from the interpreter menu at the bottom right. Here, we select our board model as Raspberry Pi Pico 2 and click the Install button to flash MicroPython onto our board. After the installation is complete, we right-click on our main.py file in the left panel and select Upload to upload our code to the Raspberry Pi Pico 2. After the upload is complete, we can see in the shell window at the bottom that MicroPython has successfully soft rebooted. Our code is now saved inside the Raspberry Pi Pico 2. We can start running our project immediately by clicking the green Run button at the top or simply by power cycling the board. And finally, our Pico has booted up, and as you can see, navigating through the menu works flawlessly. Now, let's test the project together. There are 10 different projects included in the code, but we won't test all of them here. You can explore the rest on your own. Our first demonstration project is the Smart Park sensor. Once selected from the menu, the application starts running immediately. As you can see on the display, when I move the toy car closer to the ultrasonic sensor, the distance values update dynamically, and the buzzer gives real-time audio feedback based on how close the car is. Now, let me show you our second project, the Smart Doorbell application. In this project, our ultrasonic distance sensor acts as a touchless doorbell. As I bring my hand closer to the sensor, the system detects a visitor at the door, displaying a bell icon on the screen while simultaneously triggering a chime sound through the buzzer. Let's do something fun now. I'm selecting Retro Pong Game from the menu. As you can see on the screen, I don't need any buttons to play. By simply waving my hand left and right in front of the ultrasonic sensor, I can control the paddle on the display. The sensor detects my hand's distance and translates it into game movement, offering a contactless retro gaming experience. You can easily access and download all the project files and source code via the GitHub link found in the video description. Feel free to review, improve, and use the code in your own projects. To support the continuation of this type of content and help the channel grow, please don't forget to subscribe to the channel, like the video, and share your thoughts in the comments. Your support is very valuable to me. Thanks for watching, and see you in the next project.